Hi everyone, welcome to Duality Repair. This is the Carver C4000 preamplifier. Pretty excited for this one. This is my first C4000. There's supposedly an issue with this, so there will hopefully be a repair in this video. I also plan on recapping the entire unit, and I also plan on doing some exploration into some of the more unique circuitry and functionality of this unit. There's something called a peak unlimiter circuit. There's an autocorrelator noise reduction circuit, a time delay circuit, and then most intriguing to me is sonic holography. So it's going to be a very busy video, but first things first, let's see what's wrong with it. All right, so problem confirmed. If we look at the scope, you can see the top channel has a nice output of 5 kilohertz. The bottom channel has practically nothing. And so that's going to be the right channel that has nothing. So if I turn the balance knob all the way to the left, nothing changes. That's the left output. All the way to the right, you can see that the left output diminishes to 0. So that's the right channel that has no output. So that's the first thing I'm going to attack. I'm going to start looking at the schematics, and we'll take the cover off and take a look inside. Let's take a quick look at the inside of the unit. It's just a tease. We're going to get a lot more acquainted with these boards when I do the recap. For now, I'm still focused on the issue with the right channel, and I think I'm making some progress. So I found that the right channel is shorted directly to ground. If I probe at pin 1 of the power amp board, which is the right channel's input, it also happens to be the input to the volume potentiometer right here. You can see we're at almost just a half a ohm straight to ground, regardless of where I have this potentiometer positioned. So now the question is it the volume pot itself, or is it something before that pot, or something after? Well, one way to help isolate is to engage some of the circuitry that occurs around this unit. And so if I engage the peak unlimiter circuit, which is this button here, we can see we get a much more reasonable 14.6 k ohms to ground. Now if we look at the schematic, we can see that the peak unlimiter circuitry occurs well before this volume potentiometer. And so what that tells us is that the short is occurring somewhere between the input, back here, and the peak unlimiter circuitry. If we look at the schematic, really there's nothing between the peak unlimiter circuitry and the input but the phonoamp itself, which is this board right here. And if we look at the phonoamp circuitry, we can see there's really nothing on there. When everything is disengaged, there's nothing that the signal sees that could possibly be shorted to ground except for the input selector switch, which is here. So that's where my money's at right now. I'm going to remove this phonoamp board, which is attached to the switch, and we'll take a closer look. All right, I have things disassembled here, and as you can see, the short seems to have gone away, unfortunately. So I may have gotten lucky, or it just has to do with how I've disassembled the board, and the short will come back once everything is reassembled. Either way, I'm not going to worry about it at this point. I'm going to deal with that later. Since everything is kind of disassembled, it took a while to get to this point. I'm just going to start with the recap. So I think I'll probably just go from left to right. Start over here with the power amp board. Here's the power amp PCB. It's the power supply and the amplifier board for the unit. There's not a lot going on here. It's got the volume pot on the top, which I did measure. It's measuring right around 20K. And the balance pot on the bottom. AC is entering the board at the bottom left, being rectified by the bridge rectifier. We have the main bulk filter caps here. This board supplies an unregulated plus and minus 22 volts to supply power for the amplification section, which is pretty much all of this here, as well as these top 4 components on the heatsink here. These are the output transistors. It also supplies a regulated plus and minus 12 volts supplied by these 2 regulators here. That's going to supply power for the rest of the unit, in particular the op-amp circuitry. All these components look to be in really good shape, so I think all I'll need to do is replace the electrolytics. I'm also going to clean and reapply thermal compound here. It's still pretty sticky. It's not dry or cracked yet, but it's out. It's easy to do. It's just a good idea. It's probably not going to be out again for a long time, if ever. That's the goal anyway. So I'm going to get to work. The recap went well. I also cleaned both potentiometers with some contact cleaner and removed the old thermal compound. I will wait to put the new thermal compound on when I'm ready to install the board, otherwise I'm just going to make a mess everywhere. Look at the size difference on these ball caps. It's hilarious. All right, on to the next one. The time delay board is up next. And the goal of this board is to give you the perception that you're in a much larger room than you're actually in when you're listening to your music, particularly for the spaces to your left, to your right, and behind you. You can imagine that if you're in some sort of large auditorium, this is you out in the stands, and you're listening to your favorite artist up on stage, you have sound waves propagating from the source in all directions. The shortest distance, the sound that you're going to hear first is the sound waves directly from the source to your ears. But you're also going to hear, at a delay, sounds that propagate and reflect off of the auditorium walls. The larger the venue, the longer the delay. And that's what gives you the perception, the idea of the size of the space that you're in. When you're listening to music in your listening room or your living room, you lose that effect because you're hearing the sound from your surround speakers, maybe one behind you as well, at the same exact time as you're hearing it from the front. So you can tell that you're in your listening room. What the time delay board does is it adds a delay, either 16 or 25 milliseconds, and adds a delay of that amount of time from when you hear the sound from your surround speakers compared to when you hear it from the front speakers. So you're going to hear the sound from the front speakers first, as you would in an auditorium, and then you're going to hear the sound from these speakers 16 to 25 milliseconds later, and that's going to give you the effect of a much larger space. So how much larger? Based on the speed of sound, it should be something like 18 to 28 feet between you and the speaker. That's what it's going to sound like. So you're increasing the size of your room to 40 to 60 feet wide. Pretty impressive effect. And so how does it do this electrically? Most of the schematic is just op-amp circuitry, nothing too interesting. The heart of the delay circuitry is occurring in these three packages here, specifically this SAD4096. This is something called a bucket brigade device. This is not anything I've ever heard of before today, so I had to do some research. It sounds like effectively what this is a series of many, many capacitors, 2098 in this case. So we have the audio signal coming in. It's being stored in that first capacitor, and it has to be passed on to every subsequent capacitor until it goes through all 2098. And each capacitor only releases a signal at the pulse of a clock. So you can imagine the higher the frequency of a clock pulse, the faster your signal moves through this device, the lower the delay, and the inverse is true as well. The clock pulse is being controlled by this 555 timer. It's driving this package here, which is a flip-flop, which is driving the bucket brigade device. Pretty interesting. There's something else on this circuitry. Carver calls it echo density. So when you're in a large venue, of course, you hear the initial sound from the source. You also hear the initial reflections off of the auditorium walls, but you're also going to hear additional reflections, which you might call echoes. And so they're incorporating that into the circuitry as well. We have our delay output initially coming into some more op-amp circuitry before being sent out, but part of it is also being sent back to the input. And so that's going to keep refeeding, recirculating the cycle, effectively giving you some reverberation or echo. And you can control the amount of echo, the echo density is what they're calling it, by a switch or a control knob on the front of the unit. So the board itself, just like the last board, looks to be in really good condition. Let's look at some of the chips. So most of these are op-amps, op-amp, op-amp, op-amp. Here's your 555 timer. Here is your flip-flop. And here is the special device. This is the bucket brigade. And it's socketed. I wonder if it came like that. This is the only chip on here that's socketed. This looks to be original. It's Redicon. I had to look up the data sheet, and it is available. The data sheet, that is. But I'm curious if they're all socketed like that, or this was replaced and someone replaced it with a socket. That looks original. It looks pretty clean. So it must be original. Yeah, I don't know. They must have expected that this could fail and they wanted to replace it at some point. So again, it looks like I'm just going to probably replace all the electrolytics. There's quite a few on here. So I'm going to get to work. The recap is done, and I think it turned out really well. I performed a thorough visual inspection of all of the other components. I looked at the solder joints on the back as well. I can't find any other problems, so just to recap on this. Time to move on to the next board. Here's the tone amp board. There's nothing too exciting going on here. The main function is to allow you to adjust the bass and treble. It's got multiple switches on here as well. I won't go through all of them, but there's a muting switch. One of these switches allows you to turn the tone control on or off. Active EQ. There's a stereo mono switch and a few others as well. There's only 2 op amps on here. The smaller package is for some basic input amplification. The larger one is used in the bass and treble control circuitry. There's only 6 electrolytics on here to replace. And all of the other components look to be in good shape on the top. I did notice a few things on the bottom. So some of these solder joints appear to have been redone at some point in the past. Maybe it was done at the factory. I'm not sure, but there's some obvious work that's been done. You can see the good quality of the original solder joints, and then some of these ones that have been touched up at some point. So I don't know what's going on there. I'm probably going to remove the solder from these suspect joints, inspect them, and then just reflow them just to be safe. But it's a small board, should be a quick one. All right, the tone amp board is done. I touched up those solder joints on the back. There's nothing to be too concerned about. All right, let's talk sonic holography. So let's again pretend that you're in an auditorium listening to your favorite performer up on stage. These are your 2 ears. When you have a source of sound that's directly in front of you, the sound waves travel directly at you and they strike each ear at the exact same moment. If the performer moves off to the left, let's say, the sound waves are going to hit your left ear a fraction of a second, and we're talking microseconds, before it hits your right. And it's this microsecond delay that allows your brain to determine where you are relative to a source of sound. When you're in your living room listening to 2 speakers, you lose that ability. Your brain is able to determine that you're listening to 2 speakers and you're not in an auditorium listening to your favorite performer. This is true because the sound waves now travel from, let's say, the left speaker to your left ear and a fraction of a second later to your right. And similarly, the right speaker emits sounds that hit your right ear a fraction of a second before it hits your left. And so it's this microsecond timing difference that allows your brain to be able to tell that you are in your living room listening to speakers, not in the auditorium. So the function of this board, the hologram generator board, is to bring you back into the auditorium, to fool your brain into thinking that you're not listening to 2 speakers, but you're in the audience listening to your favorite performer again. So how does it do this? Well, it's this second sound wave from each speaker that's hitting the opposite ear that's fooling your brain. So we want the left speaker to transmit sound to your left ear, but we do not want that sound to be transmitted to your right. Same goes for the right speaker. We want it to hit your right ear and not your left. So what the sonic holography board does is it inverts the signal from the left channel, and it adds a very small delay, a few microsecond delay, and it feeds that to the right speaker. And so when the sound wave from the left speaker is hitting your right ear, at the same exact moment, the inverted signal from the left channel and at a microsecond delay is emitted from the right speaker, and it hits your right ear at the same exact time. Because it's inverted and because it's meeting your ear at the same time, it cancels each other out. And so effectively what you have is one speaker only emitting sound and being heard by one ear, and same goes for the other. And so as long as the geometry lines up, your head is in the exact location that it needs to be relative to the speakers, you get the impression, theoretically, that you are not in your living room listening to 2 speakers. You're in the auditorium listening to your audience. So where the time delay board did this for the back semicircle, the semicircle that kind of envelops you, everything to your left, to your right, and behind you, sonic holography does the same thing but in front of you. And so these two circuits kind of complete the circle around you. So how does this work electrically? Well, if we start with the left signal, it initially travels through a buffer op-amp circuit, not too exciting, but it then travels through a series of inverting amplifier circuits. So it might seem silly that it's traveling through nearly identical op-amp circuits, but they definitely serve a purpose. Number one, at the end of all of this inverting, you are going to end up with an inverted version of the original signal. And number two, it takes time for the signal to travel through each op-amp. So eventually, by the end of the line here, you're going to have a very small delay, and again, all we need is microseconds compared with the original signal. So that's exactly what we wanted, an inverted version of the original signal at a slight delay before it's injected into the opposite channel, where it can exit the speaker and cancel the unwanted noise in the opposite ear. Pretty cool, just op-amps. So if we look at the board, you can see all of the op-amps on here doing all of the magic. There's only 4 electrolytics, so this one's going to be really quick to recap. Everything else, again, looks very, very nice. Good quality. The back on this one looks really nice too. And this is a pretty interesting circuit. This is something that I'm very likely going to want to test when I'm done with this. Hopefully we can get an idea of how this is working electrically with the scope. All right, this one's done too. It looks nice. The Phonoamp PCB is up next. There's not a lot of components on here. Obviously, one of the main functions is to amplify the phono inputs. There's also something called an infrasonic filter circuit on here. That's going to filter out all of the extremely low frequencies. I believe it's usually all of the frequencies below 20 Hertz. We have all of the inputs over here on the right and the low-level outputs on the left. It's got a bunch of switches as well that allows you to select between the different outputs. This board also houses the input selection switch. This is what I was originally suspecting could be causing the short between the right channel and ground, which turned out to be false. With the board removed from the unit, I did verify that there is no short between the right channel and ground. And so if there is a short, when I do put everything back together, I can be confident it has nothing to do with this board. There's only 6 electrolytics on here, so the recap should be quick again. And all of the other components, again, look to be in really good condition. The Phonoamp board is done too. Here's another aptly named board. This is the Peak Unlimiter PCB. And the function of this board is to counteract the effects of a technique or method of processing known as compression or peak limiting, which is exactly what it sounds like. During recording or audio processing, the peaks of very high amplitudes can be reduced, which effectively reduces the dynamic range of the signal. So another name for this circuit is a dynamic range expander versus compressor. And so all this does is it searches for peaks of the audio signal, and when a peak is above a certain threshold, which is user selectable using the Peak Unlimiter threshold pot on the front, it will amplify that peak just a little bit, and that brings back some of the vitality that was lost during compression or the peak limiting process. This board is also in really good shape. There's 9 electrolytics to replace on here. Everything else looks to be just fine. And the back looks very clean as well. So I'll get this done. And this one's done too. The final 2 boards left to recap, I'm showing together because they are very much related. We have the bandpass PCB on the left, autocorrelator on the right. And together these form a noise reduction circuit. So how this works is the audio signal is continuously monitored, and the fundamental frequency, in addition to all the related or correlated frequencies, are allowed to pass through a series of notch filters, while any unrelated or uncorrelated frequencies are not allowed to pass. And so in that way it filters out any unwanted noise. If we look at the bandpass schematic to start, you can see a series of very similar looking circuits. These are op-amp based, and these are just going to be filter circuits. And so you can see the frequency that it's looking for. Top one is going to filter for 2 kilohertz. Next is, I believe, 9, then 3, 15 kilohertz, 5 kilohertz, and then a lower frequency, 200 hertz. That is going to be driving into our autocorrelator board. So this is the autocorrelator schematic, and you can see again a series of very similar looking circuits. The audio signal is going to come in, and based on the frequency that's currently present, it's either going to be passed or not passed based on the fundamental frequency. So any noise that is unrelated or uncorrelated to the fundamental frequency will not be allowed to pass. And so this is where that's happening. You can see that the bandpass control enters the circuit here. So we have the negative control for 2 kilohertz and the positive control for 2 kilohertz up here. And the same goes for the rest of the circuit, 3.3, 5.4, 9, 15, and that smaller one there, 200 hertz. So again, a lot of op amps, a lot of capacitors and resistors doing a lot of filtering going on here. This is another interesting circuit, probably another circuit that I'm going to want to test. If we look at the boards, these are looking really clean as well, just like the rest of the unit. Everything's laid out really nicely. Quite a few electrolytics to replace. It's got one on the back as well that goes across the power pins of one of the op amps. That will have to be replaced as well very carefully. And the correlator board, very similar, laid out really, really nice. This too has an electrolytic across the power pins of one of the op amps. Unfortunately, when I brought this over to the table here, this connector broke off. So you can see the 5 pins. It was very, very fragile. And I thought that was going to be big trouble because I wasn't sure if I would be able to find these anymore, but unfortunately they're still made. It's a Molex connector, and you can get them probably from a lot of places. I can fortunately get it from my favorite DigiKey, which is in state here. So I ordered 3 or 4 of these. I wasn't sure if the rest of the boards might have some of these that are brittle as well. It might break off. The rest of the unit uses a few other types of connectors as well, the same type, but 7-pin and a 10-pin. I ordered some spares of those as well, just in case I break some of those off as I'm reinstalling all of these boards later. The bandpass PCB recap went well. I took my time with the capacitor on the back. I think that turned out well. The autocorrelator board looks good as well. And so I'm finally done with the recap of this unit. Feels really, really good. Once the new connector comes in for the autocorrelator board, I'll get that installed, and then it's time to reassemble. All right, I have all but one board reinstalled. It went well. They look nice. I applied some new thermal compound to the heatsink of the power amp board, and I verified that there's still no short between the right channel and ground. So it's always very unsatisfying to have a problem go away and not have a reasonable explanation for it, but sometimes that's how it goes. You disassemble something, reassemble it, and the problem is gone. If you can't reproduce it, it is what it is. The only board I'm missing is the correlator board. It's going to be a while before that connector comes in, so I did prep it by removing the pins. And once that comes in, I'll get this reinstalled. In the meantime, I am going to do some testing. As long as I don't engage the autocorrelator circuit, should be just fine. I have a 5 kilohertz, 250 millivolt signal going into the left and right channels of the aux input. And as you can see, we have signals on both channels. So I'd say whatever was causing that short between the right channel and ground was causing our issue with the right channel. Seems to be working just fine now. So let's get started with some additional testing. I think I'll start with sonic holography. All right, let's take a look at the sonic holography circuit. I have a 1 kilohertz, 250 millivolt signal going into the left channel and nothing at the moment going into the right. I think this is the best way to showcase this circuit. So I'm going to engage the sonic hologram generator now. And you can see now on the right channel, we have an inverted version of the left channel signal and add a slight delay. And that is exactly what we're looking for. So this is a great electrical representation of the sonic holography circuit in action. All right, let's take a look at the infrasonic filter circuit. So again, this should filter out the extremely low frequency stuff below 20 Hertz. So right now I have a 50 Hertz signal going into the left channel. And if I engage the infrasonic filter circuit, you can see we get pretty much nothing different. Let's drop it down to 30 Hertz. Again, nothing different. We'll go down to 10. And we'll change the range here so we can see that a little bit better. And I'll engage the circuit again. And you can see that drops significantly. So this circuit is doing exactly what it should as well. Up next is the time delay circuit. So this upper signal here is coming from the main output. The lower signal is coming from the time delay output. So if I engage the circuit, we can see we get the same signal at a slight delay. All right, the 5-pin connector for the correlator board came in, so I installed that in the board, and then I installed the board in the unit. So this is all looking really good now. It's time for the final test, which is the autocorrelator circuitry itself, or the noise reduction circuit. I don't have a great way of simulating the actual erratic and random noise, say from a tape or a vinyl record that this circuit is meant to actually reduce. But the best I can do is use the noise function from my signal generator. So I will engage the autocorrelator circuit now, and we'll see what it can do. And it does a pretty good job. So I'm pretty happy with this Carver Model C4000, the way it turned out. And it's a pretty neat little preamp with a lot of functions. Thanks for watching.